In last lecture we saw how to design a filter according to a given specification. Of course, these specifications are not just arbitrary, but they're there in order to help the filter accomplish something in a particular application. So let's look at an application example. In this case, an application example of denoising a signal. So we have a desired signal x of n that we want to obtain, but we cannot measure this directly, but only subject to measurement noise. So what we can obtain is the signal y of n, which is the sum of the desired signal and the measurement noise. And what we want the filter to do is to try to recover x of n from this noisy version as good as possible by convolving with the designed filter's impulse response. So when we have the notion of doing this as well as possible, we need to try to introduce some additional modeling assumptions so that we can define what we mean by good. And the classical way of doing this is to model all of the signals as wide-sense stationary stochastic processes. And what this allows us to do is to define the notion of a mean squared error being the squared standard deviation of the estimate from the desired signal, or the average of that quantity. And what the classical Wiener theory tells us is that the impulse response of such a filter it should have a discrete time Fourier transform, which is the ratio between the desired signal's power spectral density and the measured signal's power spectral density, which in this case is just the sum of the desired signal's power spectral density and the noise power spectral density, assuming that the desired signal and the noise are stochastically independent of each other. So the question now is, how would we obtain in an actual application these power spectral densities, or how would we obtain the power spectral density in general of a stochastic process? Power spectral density estimation comes in two flavors. So one is the non-parametric power spectrum estimation methods, and the other are the parametric power spectrum estimation methods. For non-parametric power spectrum estimation, what you try to do in general is from a set of samples of an observed process, so x samples x0 up to x of n, capital N minus 1, so capital N samples, you could try to build an estimate of the autocorrelation process of this stochastic sequence, or the sequence which produced these samples. And from that you can try to estimate the power spectral density. So here the autocorrelation sequence is the expected product between two time-shifted samples of the signal, and the power spectral density is by definition the discrete time Fourier transform of the autocorrelation function. Or you could think of a method that tries to obtain the power spectral density directly from the samples. But the key behind the non-parametric methods is that no further assumptions are made regarding where these samples come from, other than the fact that they came from a wide-sense stationary stochastic process. In the parametric power spectrum estimation method, what you instead do is you assume that the signal of interest x of n is the product of a known signal, or a signal with known spectral properties, so typically a white noise process, being fed through a model parameterized by a set of parameters. And from the samples of the signal x of n that you observe, x0 up to x of capital N minus 1, so the n samples, you try to estimate these parameters, and then you use these parameters to compute estimates of the autocorrelation function and the power spectral density. So in scenarios where you have some physical knowledge of how the signal of interest x of n is generated, this could be a powerful alternative to the non-parametric unsupervised power spectrum estimation methods. However, we'll focus on the non-parametric methods for this lecture and discuss the parametric methods in the next lecture. So to summarize this introduction, so power spectrum estimation is important because it helps us to define optimal designs using a stochastic motivation. And most advanced signal processing methods that you will come across are of this type, so based on some stochastic assumptions. And there are different types of spectral estimation methods. So we have the non-parametric methods that we'll discuss next, and we have the parametric methods that we'll discuss in next lecture. And typically you will need some added assumptions regarding the stochastic processes, like ergodicity for instance, and we'll make this throughout without mentioning it anything further.